Okay, let's start. The quiz is anonymous, but because only you filled it, yeah. So we can see the results. The Bitcoin is actually decentralized and distributed, correct? Yeah. Because function is spread across the nodes, and because it doesn't have single authority. Yeah. We need some first flip, immediate and better dynamic behavior that combine well. Actually, we need interpreters because of portability of the code, not to compile to end platforms. Do you remember? We had this in first lecture. Yeah. Okay, Java. Okay, so.
Java with VirtualBox, I did the homework. It was not the same as the virtual machine.
Right. So that's two different concepts, right? But the naming is the same, but Java Virtual Machine is interpreter, just called Virtual Machine. But that's actually JIT compiler. So why do we need to OS? Let's run, because too complex to run this whole program directly. Okay, that's partially correct. We need OS to abstract the computer resources and manage it. But that's exactly the answer, right? Biggest problem in modern. Okay, there is no correct question, correct answer to this question. So, yep, heavy bloatware is kind of the problem we have. Okay, interesting fact. So I could remember you wrote about the bees, right? Yeah, that's very kind. Okay, let's proceed with today's lecture. Actually, let me check. Yeah. Okay, so on previous season, right? We had this one, quality of service. We compared the monolith and distributed. We compared the grid cluster and cloud. We talked about how computer executes the programs, like how it does switching, right? And interrupts, preemption. Do you remember? Okay. We talked about general organization of operating system, the real-time operating system, the easiest one I can think of. We talk about what kind of problems we have with the operating system design and the binaries distribution, and the answer to that was virtualization, right? Yes. And you had the homework, you did it, great, thank you very much for that. So in today's lecture, only multiprocessing, because the networking we will touch, we will proceed, when we will proceed with the Docker, we will touch multiprocessing. Okay, so we talked about how computer switches the task, right? And the problem with that, we don't, like on a single core, we don't execute any task in parallel, like in the same time. It's like switching between all the tasks in time, right? So
as long as there's one CPU to every parallel.
Right. But on multiple CPUs, we can run tasks in parallel. For example, this one, right? Those two. But the general idea, we have two instructions which are executed on the same time, around in the same time, on different CPU cores. We can have the concurrency under one process. We can, like under one CPU, we can have a concurrent processes, right, for each of the cores. So going further to definition of this thing, concurrency, right? Multiple tasks competing, right? They want to grab and occupy the resource, same set of resources. It could be network, CPU, not only CPU, okay? And parallelism is our tasks are executed independently on separate time domains, right? On separate resources.
They don't have to compete.
Okay. So because of in general, we have this limitation of our computer architecture. Do you know the name of this guy who designed?
Apple? What are you going to say?
Who designed the modern computer architecture in 1945? We actually use around like Harvard architecture, but von Neumann.
I don't know.
You haven't heard? Okay. So modern computers are built on von Neumann architecture. And because of that, they share the same addresses, same bus address for, do you know the bus, right? buses like?
We did it in networking, they have the same address for the data.
Right. So the data and the instructions of the program lie in the memory, and because of that we have it has to separate this bus between. Do you understand what I mean?
Yes,
Okay.
I'm reading that as well.
So because of that we have fundamental two blocking mechanism, right? We can lock the CPU power. If some task runs on the CPU for very long, for example, we compute in the Bitcoin hash, right? It requires just the CPU cycles. CPU doesn't stay idle, it just tries to solve our task. That's a CPU-bound process. And we can have, for example, a network call, right? To fetch some data, download the file. And in terms of the speed of CPU, that could be extremely expensive. Why? Because okay, so CPU runs on 1 gigahertz, right? And if the request, average ping to America, for example, United States?
I do not know the address to America.
Like 100 milliseconds a gen. So let's count. We have 1 gigahertz, one core, right? And how many instructions do we skip if we just wait for response from America? 200 milliseconds, because 100 milliseconds here and there.
Yeah.
So
many things, so many operations can be done in those.
correct. Thanks. So that's kind of problem with the IO-bound tasks, right? Input output. It could be not only in the network call, but also reading from the file. Maybe some other process blocks this file. It already opened the. We wait for resources to free, and all of those are called IO-bound tasks. So let's see, right? And because of that, we can have a bottlenecks. Two different kind of bottlenecks. Why? You see, the bottle, and it has a neck, right? And the neck doesn't allow traffic to pass freely, right? So we have a congestion here. And the kind of how to optimize your program. You have a.
You have to open up the bottleneck. You have to free up the space.
The most interesting part is to find it. You need to find by profiling, right? You need to find where your program spends most of your time and try to optimize that thing. Okay? So that's kind of problem with the bottleneck. And it's not titled. Okay, so the problem is we have CPU bursts, right? And waiting for input output, while the Linux socket will respond. This is CPU bound task, right? And that's IO bound. We have plenty of CPU jobs, but not too much. We just wait for something to happen from external world, right? So that's a comparison. But we have discussed all this, right?
Yes, we did.
Okay. Let's go back to multiprocessing. So, for example, we have two processes, right? And from the Linux or Windows OS kind of thing, the process has its own process cache and the registers, and it runs on the you see CPU registers, stack pointer, the operating system requires a lot of memory to support the process running. But inside this process, important thing here, process is totally memory isolated thing. This memory couldn't be used in any other process. There is kind of concept of shared memory between processes, but it's difficult to deal with. So in general, process is isolated. And we have primitives called threads, which can run also in parallel inside one process. And they could share the same memory.
I know those, you use them in programming to write concurrent programs. I hate them.
Correct. But not only concurrent, because threads are also not competing for the resource. They kind of compete, but we will talk later. Because it uses the same memory under the process, right? Threads using the same memory. For example, process 1, process 2. Those threads use one memory map, right? One set of pages. And this one uses the separate isolated one. And there is also kind of coroutines, but we will talk about this later. So three types of multitasking, right? Processes like isolated in memory running job, right? The thread is also a parallel thing, but it shares the memory inside the process. And coroutines. So the threading mechanism in operating system is very expensive.
Wait,
Right.
it says our programming language primitives, so like int, log, string, those primitives, or no, not strings, but those things.
Operating system has own primitives.
Oh.
Like, okay, so what do you mean by programming primitives?
Like every programming language has the int, char, double.
But that's types we just describe layout in memory, right?
Yeah.
So for example, int in C there is no standard for int. Do you know? No.
It's dynamic.
No. It's hardware dependent because C runs on so many platforms. If you run on like Arduino, int would be maybe 16-bit. But on this CPU, like on modern CPUs, it would be 32-bit standard. Okay. So the problem is OS has its own like types to describe this memory layouts. For example, for threads, because look, we need some service information to support, like just to operating system. Do you remember the scheduler, right?
Yes.
Which switches
yes.
the. Right. So for scheduler to work, we need like some address space and memory, which is designed for operating system to understand what you are running. Okay. So that's not the memory of the program, but some structure with which OS understands. Okay. So that's similar to primitives in programming languages, but it's like a OS level primitives. But the analogy is great. So those two are okay. If we spawn processes, it will occupy memory, right? Because we cannot share it. The threads won't, but the mechanism of how threads are run, like how threads are used, is kind of expensive.
Because they're parallel.
Not only because operating system is designed to handle so many types of threads, like so many types of jobs, right?
Yeah.
And this mechanism is really expensive because inside one process, thread would compete not only for they will compete with all other threads running on your operating system, and because of that, there are like actually many stuff is because of the bloatware written. Like operating systems are written in a bad way, and because of that, threads are slow. Because of the scheduler is very slow for some reason, I don't know. So we can implement. Have you heard about event loop? Something like that. Coroutines.
By event loops, do you mean like a certain process that will always happen, like in 4 milliseconds, it should happen again and again? Do you mean those?
Not exactly. For example, in JavaScript, when you run your browser, right?
Yes.
It runs the infinite loop, which updates the elements on your on your screen.
Yeah.
Okay. So in infinite loop, but it kind of switches as a threads does as a concurrent way,
Yeah.
in a concurrent way.
Would give multiple operations.
So we can implement not parallel because we don't use multiple cores, okay? But the switching inside the program, we can implement in the programming language we write, okay? So there are many libraries, like Go has Goroutines implementation. Python has fucking insane number of libraries. Green threads, async.io, lightweight threads, that's all like from Python. From JavaScript, event loop, UV loop, tasks, like all of those are implemented on the programming language. It's like
So normal Java loops, the normal loops.
no.
But like similar to them, similar to those loops. Similar to the normal loops, like if the
No. It works in different way, okay? So because they tried to event loop is from JavaScript. It's just called that way because it's like switching between the asynchronous tasks. So those running only concurrently, not multi-core, only concurrent execution, so they are switching. And the problem with that is they are implemented on the programming language.
Yeah.
And because of that, they don't use threading at all. So they are not parallel. But they are fast. For example, how many processes you can have on a computer? Well, maybe 1, 200, and then you will have the memory exhausted.
Yeah.
Okay. How many threads you can have? Maybe 2,000 to 3,000 threads. And after that, you will have the scheduler stuck. They will switch too long, okay? Maybe 5,000 is also fine, but not that much. This you can spawn million of coroutines because it's written on the language you're using, and it's done in an efficient way. And because it's not parallel, it doesn't have to worry about much thing the threads and scheduler do. So, wait, we will go back for a second. Okay, that might be the best. So if we have CPU bound task, the best way to optimize this one is to make it parallel, like parallelize on multiple, like do this thing in parallel, this thing also in parallel, right, on different cores.
So nothing is wasted.
Right. So, but with this thing, you can, because here you're accessing different resources, right, in memory. For example, for computation of some kind. But this thing doesn't have to be parallel. Why? Because when it can run on a single core. Look, if those are different tasks, for example, okay, I need to parse the content of 100 websites. How I can do that? Make a request to the website, wait for its response, right? Make another second request to second website, wait for response, right? Or I can make these things in a sequence, make requests, make all the requests, and while I'm waiting for one,
Have another one.
right? Because waiting doesn't require the CPU time. IO bound tasks doesn't require CPU time, so we can do but it's still okay.
That's why they're fast.
How clear is that for IO bound we can do concurrent, not parallel?
Yeah, I got it. That's why I was faster than CPU bound tasks.
Right. So with this thing, coroutine can help, right? Because it's efficient and we do concurrent way of. So we can send thousands of requests and just wait for each of them and just switch and check which one will come up first, okay? So, but the request will happen in parallel, but the CPU instructions will happen sequentially, like do one request, do second, third one, okay? That's clear,
Yes.
right? Okay, so for CPU bound, we use processes and threads. For IO bound, we have threads and coroutines. Okay, you might ask me what thing, right? And
I think that's very rude.
where it's applied in practice.
Okay.
So we will code. Let's write some code and see in different languages.
Should I turn on the
Can you sit? No, can you sit here? I will. That's like live coding. I will code and you will. Yeah.
Always wanted to feel like the task manager.
What?
Always wanted to feel like the task manager.
Wait a second. Okay, so I assume you know programming a bit, right?
Yeah.
Okay. So you will understand the structures and basic. Can you see it
Yeah,
well?
yes.
Okay. I'll create just test directory and we'll write some C code. For example, there is a library called RayLeap. It's pretty good for graphics in C. And because we use operating system primitives, we also need to include this memory mapping for threading, okay? So we will use the threads for now. Okay, so what we're gonna do? Let's assume we are fetching the state of some sensors. And we need to just take the state and switch the state of something, just, okay? We will implement this as a colored rectangles. So let's first define the structure of those rectangles. What we need is maybe Haze, Wise, and X, Y coordinate on the screen. We need the color of rectangle which will show the state. Let's call the structure just maybe R for simplicity. We need the array of those rectangles. So in C it's done in like following way. For example, we'll have 400 of those. Okay, if you have any question on the code, just ask.
Yeah, just waiting to see.
We need to create the window like this. So that would be example of race condition. So let's display the rectangles in the grid. So we have like maybe 40 by 20. Okay. So just in the loop, I'm gonna initialize the parameters of rectangles. We have 40 rows. The size of the rectangle would be maybe 18 pixels and 2 for padding inside. Not that much. So for Y, I think the same, right? And Y is 18. Haze is 18. And the last one is color. Okay, so we just cast the type here from 0. It's just cyan, I think. Red, green, blue. Yeah, it's kind of cyan. So we need to initialize the thread, right? The worker. And we will have one thread by default, the main one, because we run the program, right? Like the main thread of the process. But we need a second one. Here we need to pass the worker function, which will be executed by this thread. Something just RayLeap needs. We need to set up the FPS, and while the window is not closed, it should close. We set background to black, and in this for loop, let's don't have one, we have 40, 400, right? we just need to draw the rectangle. Okay. X. And we pass all the. Previously, we defined the size and position of each rectangle, so we just need to pass that one here, like X, Y, white, and haze, and color. Right. And we need to end the drawing procedure. And to wait for thread to finish, we just write the thread join. Yep. But that's not needed, actually, because we won't exit in the normal way the program.
I'm very sorry, but can you, like, I have some questions about
Yeah, sure.
and I don't know the language. Can you please, when you wrote can you please,
Upper or, okay.
Can you please
Yeah, sure.
Sorry.
Sure, sure.
So like you created the type, the construct, right?
Right.
You created the constructor for it, and then you gave it the number, right?
That's an array of.
That's an array. I know.
Okay.
I'm like what?
Yeah, that's array of those structures. The structure just describes
And you gave
the.
this is made of like 400 of this, right?
Right. Right.
And then what we did, you did this, not what you did this, but like, when did you define begin drawing and close end drawing? Like, are those automatically here? Or did you define them?
That's from Rayleigh library. That's how the graphics library works. That's because I need just to showcase this. But actually, what begin drawing does, it starts receiving. How to explain? Okay, sorry, just don't mind. Okay.
Yeah, okay.
So that's not too complex to understand, but the begin and end drawing is just formal things that we need for Rayleigh to work.
Yeah.
So let's run this thing. So just to compile this thing.
Извините, конечно, за беспокойство. У вас ручки лишние не найдется?
А вы вернете?
Наверное, да. Это не мне надо.
Ну тогда, ну 100% верните.
Хорошо.
Сейчас, да?
Да, у нас сейчас корона из-за этого. А, ладно, если вам нужно.
Ну это не моя просто, понимаете? Свою бы я отдал, мне не жалко. Это тоже мои студенты. Okay, so okay, I need to compile this thing. A second. How the example1.c. Example1.c. That would be just a1. But look, we haven't created a worker function here. When we start the thread,
Yeah.
we need to pass some function there, which will run in a parallel, right? But this function, because it's thread, it will get the access to all the global variables from the process. Yeah, this one, like, I named incorrectly. Rectangles, right? This is the global variable. It exists in the process context, not in the function scope. So if we create the thread, it will be able to access this memory. Let's try this one, okay? So 1 second. Okay. It will receive one parameter, just arguments, but don't worry, we won't use it. So it will also have the infinite loop. Like this will run forever, okay? and we should go through all the 400 triangles, rectangles, and change the color. So, for example, if rectangles I color green is 228, because we sent this, then we need that to be changed. Zero. Let's switch to blue one, like more blue.
Do you have it memorized?
What?
Do you have the color codes memorized?
Not really. I have, how to say, I like, I already wrote it before, because,
I didn't notice, so I just thought you memorized the colors.
sorry, I'm not that smart, but it's actually easy, like, red, green, blue, right? So, maximum value is 255. Why? Do you know why?
It's black, right?
No, so those are 4 components,
Yeah.
okay? This is actually alpha channel, the transparency, but never mind, we have like red, green, and blue, right? But the maximum value is 255. Why so? Like,
You said transparency, so like the darkest color is 255?
because the color is saved in the 8-byte format.
Oh.
So per each we have 2 bytes.
Oh, got it.
No, I'm lying. For each we have. Okay, so 8 bits.
Yeah.
So okay, 4 bytes format. This is 4 bytes format. 32 bits per. So those numbers could be put into single integer. 32 bits.
Okay.
Each of like color part, right, is 8 bits. So we cannot escape the 8 bits. So the maximum is 255. So that's just if you're curious. If not, that's fine as well. So we can just switch it. What does this function? It will run in parallel, right?
Yes, it will run infinitely, and if
Right.
it always changes color for every single rectangle.
Right. So if the green part of is, so we just switch from green to blue. Every time we go through all of the rectangles and just switch their color. What should we see? We should see the rectangles,
And different colors.
and it should blink, right? Simultaneously, because this function changes.
Right, simultaneously what happens in the same place, so it will change and blink. Right?
Let's see. Blink. And
Because you didn't specify that they should be next to each other, so they'll just be in the same place.
correct, but we'll see what will happen. Because we set 228 here, and we set the green here, so next time it will switch back. Okay. So I think that's fine. It should compile. Nope. Too many arguments to function draw rectangle. Let's see. Draw rectangle. X, Y with haze color. Not too many. Okay. Well, that's bad. Okay, I missed something. Yeah, here. I know. No, sorry, we should recompile and run. Okay, we see this blinky stuff.
Yeah.
And what it does it tell us? That we have two threads inside single process. One displays the main one is used just to display the rectangles, right?
Oh, and the thread is used to changing colors because it accesses everything, global information.
Right. And the second thread is used to switch the colors. But because we have no synchronization between the threads, the one thread which draws it can access the memory in the time the second one is maybe the half of its way changing the rectangles.
Yeah, that's why it's like that.
That's why it's blinking. But we expect it to change simultaneously all the rectangles, right? Okay, so In distributed systems and in centralized one, this thing is called race condition. Why it happens? We have two separate threads, right? For example, we have two persons and a bank account, right? Both persons read in their memory, they read the value of something, right? And both of them are incrementing and putting it like to account the.
But one is faster than the other.
Yeah, but because when the person A has reached the info and person B, they haven't wrote into it. We expect it to be 19 here because both person A and person B send requests to increment, but because of the race condition, we incremented only once. So, for example, I'm checking my account to pay, okay, and because payment. I'm doing two payments, and because payment one haven't finished, the other one like read the same number from my account, and like I pay it only once, but I made two payments. Okay, so that's very dangerous thing. So the definition, right? The substantial system behavior is dependent of the sequence or like the timing of execution. This could be because, look, if person B will wait until the person A will finish, the result would be different, right?
Yes.
Of the same operation.
But because I didn't wait, now we have an error.
Yeah, we have inconsistent behavior because in our example, we don't wait until the first thread will finish and we are reading inconsistent state from the main thread. And that's why it's like randomly goes insane, right? So what we can do? We need to synchronize the threads somehow. We need to say, okay, for one thread to stop and for other one to have a green light, like have like how it's called?
So we're just writing thread sleep, right? I think we're writing thread sleep for that.
Not really. Like yes, we need to suspend it somehow, right? But it's called. Okay, just we need to give it the like permanent and isolated access to resources. Okay. In our example, what the resources we share? Like what is the shared state?
So this is the rectangle constructor and the color changing method.
Actually, yes.
And also the array of 400.
Yeah, but actually, what our problem is, right? What we need to protect is the array of, because structure is just the language description of the memory, and the actual memory, which is like lie down and is the rectangle array.
Yeah.
So for this one, we have mutual exclusions or mutexes. For you to understand, okay, this is like professional. I think like logicbig.com is kind of, they claim themselves professional programmers, but even this contains like an error. So many programmers don't know what is that. Like critical section does nothing about like that, because critical section is about having no interrupts, like switching. But switching is present here, even if we use mutual exclusions. Like just for your understanding how bad the programmers are nowadays. Okay. They just don't understand the fundamental things. Like I just intentionally pasted it here just to show that it's insane. Like critical section does nothing about this. However, somehow someone calls this critical section.
Critical should not be interrupted ever, right?
Right. If it's critical, we should suspend all the system interrupts, all the preemption between, even to the system one. But if we use mutual exclusions, okay, let's talk about mutexes. So mutex is this one. It has two states, green and red. We know that if it's red, okay, right. So someone made it red, okay. So it could be locked or open, like acquired or freed. But the general idea here is we can, initially mutex is like free, okay, it's open. But we can, from any thread, we can how to say?
Lock it to make sure the thread does its job, so it's not interrupted by
Right.
another thread.
Not kind of that. Look, so when we signal the mutex,
Yeah.
it becomes locked.
Yeah.
And all of the threads, there is no possibility of race condition in the mutex because it uses the special OS instructions, which done. Look, if I'm writing to some variable,
Yes.
right? How many cycles of processor does that? Like,
If I give a variable,
for example, I want to increment the variable.
yes.
Okay?
It
How
will-
many?
One, right? One.
No, because I need to read the current value.
Oh, and
Then
check
add-
if it's the same, and then replace if it's not the same. Right?
I mean, okay, so we have a variable, okay? I need to read the value,
Yes.
for example, it's 5.
Yeah.
Increment to 6 and put it back. So it's at least 3 operations.
Oh, got it.
And any operation, any of that, could be interrupted by other, like we can have this
That's why
condition.
we have a mutex. That's why we use mutex.
Yeah. So mutex cannot be interrupted. It's like atomic operation on the hardware, on the operating system level. So it's whether locked or unlocked. We don't read its state. We just signal it. Okay? I will show how it works. But for example, but with the mutex we can protect single resource. Okay? For example, only the some array of some code. Okay. For example, thread 1 acquires the lock.
Yes.
Okay, the mutex, and does some processing of something, right? The second one will also, for example, we trying to acquire the same lock. It will
But
get,
it's locked because the first one already acquired it.
it will stale on operating system level. Like OS will see that thread 1 is stale, and it needs to wait before the switching back from thread 1 to thread 2. So it just won't run the code. Okay. And when the lock is released, the lock is when then it's acquired by thread 2, and this is called the critical section here. But okay, like we are running the critical section right here, the code which cannot be kind of in the scope of this lock, and then it gets released. Okay. The definition of mutex. Mutual exclusion, okay? Signaling is locking down, and releasing is unlocking, okay? Okay, I will show you something. Let's proceed with the wipe coding. Do you know wipe coding?
You use AI to close.
Yeah. Okay, so that's okay. I understand.
Sorry for
That Tbilisi is crazy place to live. I don't live in Tbilisi because of this. Do you know, like air pollution is like crazy. Okay, so let's change our code a bit. We create the mutex. It's also like this description of this type.
We don't need to write include.
This is included for this because it's already in threads.
Sorry.
Sure, that's logical question. So it's already described in threads as well as the thread start method we use. So we create the mutex. It's just some place in memory, okay? We need to use it somehow. Let's first, we need to, I think, initialize this. Mutex init. We pass the link to it. And it's just plain because there are different types of mutexes actually, but okay, and then locking and unlocking, right? This is the place where we access the rectangles, right?
Yes.
But not only. Oh, okay, because this code is done before we start the thread, okay?
Yes.
The thread is created here, so that's before we start the working function. So this is thread safe code, right?
The colors of this thread safe code because it's the color changing isn't the thread safe because it's public. It's for everyone.
Isn't the thread safe?
Yeah, it's not thread safe.
right? But this is thread safe.
Yes.
But we created the second thread, and accessing the rectangles is not thread safe anymore because other thread is changing it. So before we just associate the mutex with this array, because the only thing we care is this one, this array of rectangles,
Yes.
because it's really like the memory we access in parallel, and we just know, okay, it's not done in the code anywhere. We just know that okay, this mutex will be used for this part of the code,
Yes.
like just for
This array.
yeah. We just assume this, okay? So that's how to say. That's important to understand that there is no linkage like between this in the code level, okay?
Yeah, we just assume.
Right. Thanks. So what we do next is mutex lock. Here, before using rectangles, because we know that it's associated with the mutex. Okay, we can even do, you know what? Oh, no, we cannot do this, sorry. Okay, so we know that this one is associated with the mutex. So we trying to lock the mutex.
You misspelled it. You misspelled it. You misspelled matrix block.
Okay, sorry. Thanks, great catch. And in the end of operation, here, after the loop, we do the unlock. It's not visible. We do the unlock of the mutex. So what this thing will do? So this thing will try to signal the mutex. But if it's like red already, if it's already locked, it will, on this instruction, it just freeze, okay? And wait until it's unlocked. The problem that we can have here is a deadlock. For example, the second thread is already locked the mutex, right? And haven't unlocked it. Even if we don't use rectangles anymore, like even if the second thread, for example, there was an error in the second thread, like programmatic, and it just died, okay? And haven't unlocked the mutex.
It's still gonna be locked.
Yeah, your program will freeze just basically forever, okay? So for this we need to unlock the mutex at the end of our processing, okay? And what I need to do as well.
You unlock, wait, we locked it, then we unlocked it. We initialized it.
Okay. Okay, we only locked it here.
Oh, we need
Any
to,
other place?
we need to lock it and unlock it
In another thread.
Yes. In the not thread safe.
Right. So in between those mutex lock and unlock, we assure that no other resources are trying to access the rectangles.
Yeah.
But there might be the case, okay, if we don't put the mutex locking and unlocking somewhere, it could access. Okay, even if we locked mutex in one place,
It could access other places as well.
in other places, like for example, we have two worker threads, and we only added this code to the one,
Yes.
and the second one will also create the race condition because we haven't added the mutex, right?
Yes.
They call it between the mutexes. It's generally called the critical section, but it's not really like it has a bit different meaning. Okay, so let's run this now. Okay, you see now color changes simultaneously, right?
Yeah, because there's no race condition because it waited.
Right, because the main function just waits until the worker will finish, okay, because of the mutex. Okay, when it's used, for example, I wanna create this theme, okay? On the back of my smartphone, I want, like, when I play some music in the headphones, I want to visualize the music frequencies, you know, like equalizers.
You can make multiple arrays and then lock the color changing to those specific arrays.
Right, but the problem is, audio stream shouldn't be locked anywhere. Like it shouldn't be stuck. Because if I'm listening to music, I don't even care about this thing. Okay, I should listen to my audio anyway. But I also should see this one. So audio shouldn't wait, and this thing should wait for audio to process, and we cannot finish the audio processing. By the way, to represent the audio stream in a frequencies domain, do you know what we use?
No, I was gonna ask that.
Okay, do you know the Fourier transform? Fourier transform. Fourier. That's beautiful. If you are interested, are you interested in art? Like,
Yes.
okay, I will share the link. Okay, let me actually show you maybe some video about this. Fourier transform. 3 blue, 1 brown.
This right here is what we're going to build through this video. A certain animated approach to thinking about this super important idea from math, the Fourier transform. For anyone unfamiliar with what that is,
Picture stuff.
number one goal here is just
Okay, so let me actually. So any signal of any like wave could be represented of the sum, like a sum of sine waves, and it's not only applicable to the signals.
just picks up on the air pressure.
Um,
It only sees the final sum. So our simple question is going to be how you can take a signal like this and decompose it into the pure frequencies.
like this algorithm is super fast. Like there's a discrete fast Fourier transform which is like crazy fast. You can do it on like microcontrollers, even like low power CPU. But Fourier series.
So we use this algorithm. to-
Right. It's pretty like for example the attention mechanism now in ChatGPT works using the Fourier transform.
Attention.
Yeah, it's not like the ChatGPT doesn't analyze your text as sequential.
Oh, it converts it to the algorithm and then uses
Right,
it as
as a frequencies, but that's kind of complex. But like, I don't know why it's freezing like this. But so we can decompose even the picture of any kind. We can decompose into like a Fourier transforms, like in the Fourier series, and like draw something even very complex with that. So that's pretty cool. Let me show you some stuff. So for this one, right?
yes.
I actually built this thing, but I'm currently trying to do this one. Where it was? This one, okay? So first I started with like Fourier transform and stuff. Let me show you.
I can just stop.
No. No. Okay. Okay, I can find it right now. Anyway, so mutexes are heavily used there. Like in this project, even if you're using like microcontrollers,
Yeah.
you install the free real-time operating system on it, and you heavily use mutexes here because
It's
Again.
a control movement, so you need it.
right, you cannot decompose audio stream in live by Fourier because it's pretty heavy algorithm. It's fast but pretty heavy. So you need to cache a bit of audio in like a head, pass it to headphones back. So it's a bit complex. No, actually, let me find it. Where it was. Yeah, this one. So kind of way it works there. You can see that it's kind of like pretty complex. For example, this is Fourier transform written, but inside we have the mutexes and kind of stuff. Maybe I can run this one. Okay. I don't know. Like this. So this written algorithm, right, of decomposing. So it's really like you can build beautiful stuff using a pretty simple, how to say, like using C and yeah, and simple primitives. You can build very good stuff, like high quality. So the next, do you know what is a queue, right?
It's if I have multiple tasks, is it first come, first out, or
First in, first out.
first out?
Great. So just to, like, we have some buffer in memory, pre-allocated. For example, 100, because it cannot go infinitely, okay? But the purpose of that, we can store some objects, for example, tasks or anything, right? We add this in the end of the queue, in the tail, and when we, like, for example, CPU is free, it dequeues the first one task from the queue, right? So, and we can have a, that's the definition you correctly said, like first element in, right? By the order would be the first element out. Okay, sorry. So there could be different things like priority queue. We can have a priority inside, like tree, and like it's crazy how complex it could be. But this is also used in distributed systems, right? Queuing, because if we cannot process the tasks in real time, we can store them and process it later. And maybe, like, just an example, if we are not getting much results, we can reverse the queue. So take from this side, like different optimization techniques could be, right? So the other thing is pipes, but it's related to multiprocessing. This wouldn't be on exam, you see. So the reason we have pipes between multiple processes, which are isolated, we can have a unidirectional communication channel, right? We can communicate between processes, but that's very expensive because we send it to operating system. Operating system serves it to the second process. It's kind of very complex and resource intense, right? So, and we can have a shared memory, which is also kind of, we can have a shared memory between processes, but that's also kind of complex to deal with. And what is built on the queues, right? We can build a pub/sub model on that. For example, we have multiple submitters of the jobs. For example, we have 5 threads which submits some kind of jobs, right? And we enqueue that into, like, basically queues. So the queues for multiprocessing will have mutexes inside, right?
Yeah.
Because it's accessed by, for example, multiple publishers could access 2 different queues simultaneously, and the subscribers are also called the workers. They take the tasks from the queue and execute it, and put the result back. For example, in pub/sub, the publisher here and subscriber here, but this subscriber could be the publisher to another queue, right? And this is good practice to have only one publisher per queue, okay? Only one. So, and we can have another way of doing this thing, right? Distributing the tasks between processes. We can have an actor model. Just imagine, sorry. So instead of the pub/sub, right? This is kind of thing that we use to deliver the tasks, right? From the source to destination. But this is used in distributed computing as well. And this one, an actor model, is also well used when we have a direct links by the network or by the, like, using the queues and mutexes. We can deliver the tasks to different processes, like in a decentralized way. Okay? So, for example, this actor could send the messages to different other, right? So, but this mailbox is also a queue because this can send the multiple messages, and we need to buffer this.
So it's never one purpose. They always have multiple purposes. The mailboxes and the actors, right?
The mailbox is a part of the
Yeah.
actor. So the mailbox is just
They're all
the point of
connected to each
receiving.
other.
Right. But inside we will also have, for multiprocessing, we will have a mutex for synchronization, right? Okay, so I think that's it. But before, I want to show you some interesting stuff in Python if you have some time. Any questions on that?
No, I understand.
Okay.